Welcome back. Today I'm going to explore a number of obscure additions that show up inside of regular story problems and what they mean to the integral calculus and the differential calculus more broadly. The key idea here is that there's really only one measurement that we care about, measurements that distribute. Once we fix on the distributive property, we lock in a lot of essential qualities about addition, but not as many as you might predict. Nevertheless, we can use this to explore calculus in a number of different applications, both conceptually and arithmetically. Let's get started by reminding ourselves of the basic principle. The basic principle is that we want to take a shape such as this larger rectangle and make it be the whole, be the sum of its parts. Here I have two parts, green and purple. By defining area as length times width, I can attach that meaning to the distributive law. This length is a plus a prime, and that width is b. The product distributes, and therefore the whole is the sum of its parts algebraically, and therefore also in the integral calculus sense. It also works horizontally. We can take length times width that's divided into two parts and distribute on the other side. The distributive quality of multiplication is what gives us the access to the integral calculus as an arithmetic tool. I leave it to the philosophers of math to explain why that should be the case. At this point, the numbers just match up. As we move to shapes that are less like rectangles, it requires us to cut up the pieces into rectangles and associate them back to the rectangular measurements. Otherwise, we don't have access to this distributive law. We do that through the method of limit. All we need is for this approximation to be true for all but finitely many values of n. We can throw out the initial cases that didn't work out too well. Once we know that for all but finitely many of them we get within this precision, we know that eventually everyone will come up with the same limit L. Once more, I leave it to the philosophers of math to decide whether that's actually the meaning of the area under the curve. There may not be such a thing, but there is a number that comes out of the integral, and I will call it the area. What I've drawn here is the sum of two functions, f plus g. That means that every input I take the value of f and the value of g and I add them up, making a taller column. I've tried to keep the color coordinations the same. The result should be somewhat transparent. We should be able to take these two areas and add them up, and in fact that's what's happening here. What this means as a formula is that if I add this integral plus this integral, I get this integral. We like to write this as a straight line in the following simplified form. Two words of warning here. I've started to become lazy and stopped drawing the f of x. I've just called it f and g. Some professors even prefer that. It's a matter of choice. I just want you to see both methods. The second thing is that it's tempting to want to call this the distributive law. After all, this integral symbol seems to have distributed over f and g. Mathematicians have another name for it. They'll say something like the integral is linear. I'm in two minds about this. When I was a young professor, I was quite militant about describing this as linear, so that it would connect to a later subject called linear algebra. But the more I've worked on these things, I've realized the distributive law is at the heart of why it works. So why not acknowledge where it comes from? I'll let you decide what you need to do, and in particular, if you're taking a course on this, you should ask your instructor as well. So whether you think of this as a distributive law or some new rule called linearity, start to memorize this formula. But wait a minute, there are actually two types of distributive laws. Where's that one hiding in our integral? Here we have a way of describing the distributive law that we see over here, the horizontal version of this rectangle. What we see here is that we have a single graph f on the top, but we've subdivided the intervals from a to b and b to c, so we have a horizontal value. Now remember, what we do when we do this integral is that we approximate it with rectangles underneath. We might have in fact had one initial rectangle. That initial rectangle was subdivided here, and therefore its area would be the sum of this part here and this part here, forgetting about the stuff above. This is our first approximation. It's not as accurate as our limit will eventually get. It's just a getting started. That is exactly the distributive law that we needed over here in the horizontal form. What we could then say is our first approximation of this integral is this one, and the second part is this one. The fact that they're equal is our good old-fashioned distributive law. But now something strange has happened. Over here, we distributed over an addition. What are we distributing over here? To see what distributes, it helps to write our intervals with sets. What I've now done is separated my two integrals. I have the integral over I and the integral over j. Now, what would be the right notation for the integral over both of them? It may be tempting to use the union. After all, it is the union of I and j. But there's a subtlety. What if I choose to use the same integral more than once, such as I and I, or I have I and j overlapping? If I do these separate sums, the overlapping parts will be counted twice. Therefore, my integral won't be as simply the union. It'll be the disjoint union. This is an incredibly important change in what's happened. We're pushing our distributive law to the limits here. We started with the distributive law and our regular arithmetic rules, but now we're saying the distributive law has shifted into the domains of integration, I and j. And intervals don't have a notion of addition, but they do have a notion of disjoint unions. And that's precisely what we need to do the distributive law here. The distribution here is over the disjoint union of these spaces. This should start to tempt a question in our minds. If we're willing to turn our addition into disjoint unions, then what other types of addition would be appropriate to have distributive type calculus? That is, what is the whole the sum of its parts? What is a sum? We're pretty lucky that the distributive law seems to match what we see in the visualization of this area. But why would that be true in general? And what if our concepts have to vary? In fact, even with the integral, we start to benefit from some generality. For example, what if the function f happens to dip below the x-axis? When we create a formula to work out the integral, it helps incredibly to just use the height as the function value. That is, what is f of x times the thickness? But if this is our formula, we run into trouble as soon as our function becomes slightly negative. We don't typically think of area as a negative value, even though this formula will now give us negative values. Now, there is a way to fix this. We could take the absolute value of our function f, but that could change our formula and make a lot of extra work. And scientists have found that, in fact, there's already a use for the negative areas. We could instead think of this as energy. How much energy is trapped inside this function? We could say here it's borrowing energy. Maybe it's a debt. And over here it's paying it back. It has a positive. So if we take it together, we take the net energy. We'd add the negatives and the positives to see how much was overall. This is an important addition. We call it potential or energy or other words. But it's an idea of taking area one step further, adding negative signs and making it a conceptual leap. It no longer has to be area, and yet the distributive law still works, because multiplication can distribute over negative numbers as much as it can do it over positive numbers. So we start to see that by bridging our concepts to new number systems, what we really need to maintain is the distributive law and nothing else. So on the board behind me are two ways to represent the very same product. I'm taking length 1 plus length prime and w plus w prime, and I'm multiplying those two values together. If I was to multiply them up internally, I would end up with 4 different values. L times w would be that first area, L prime times w would be this bottom area, L times w prime would be here, and L prime w prime would be the bottom corner. I need to add up all those spaces. But I have some choices to make here. Do I first divide up the rows, or do I first divide up the columns? Whichever way I do it gives me slightly different formulas. And it's the same thing as what we're doing with the distributive law here. As a word of caution, you may have been taught something like the FOIL method, first, outers, inners, last. But that makes a lot of assumptions about additions, and therefore I don't want to make any choices like FOIL until I'm forced to do so. In fact, I'll just follow the distributive law step by step. On the left-hand side, it's as if I took the w's and distributed the L plus L prime over all the w's. I see that this is treated as one solid length times the width. Now, inside of those, I distribute one more time. On the right-hand side, I've actually split it up on the lengths first, so I do the rows first. Let's play a little matching game with what we've discovered. Over here, I have an LW, which for simplicity, I'm going to call the value A. I notice there's an equivalent there. I'll write that one in. Next, I see an LW prime. I've called that B. LW prime over here occurs right there. L prime W, which I've called C, occurs right here. And finally, L prime W prime I've called D, and it occurs at the end. Standing back to see the entire relationship, we see that A and D stay in the same place, but B and C have swapped positions. This calls for a rule between our additions. It isn't that we can remove parentheses and add in any order, but simply that the middle two terms can be swapped. This is what's known as a medial law. Medial stands for middle, which is of the pieces that are moved. This is my preferred way to think of it. Nothing actually moves in the middle. We simply move the parentheses. After all, I don't have lined paper. Nothing prevents me from writing a sum vertically or horizontally. What we're really saying with the medial law is that we can add in the columns first or in the rows first. Either one gives us the same result. Notice what this rule is not telling us is that A plus B can be done in any order. The medial law is a very generous rule because it doesn't require any of these conditions. Valuable sums that are used in everyday life fail to have these properties. So it's good that we've now landed on a rule which doesn't require them, but still behaves well for integral calculus. That is, we can subdivide the pieces in any order we want and still get reliable answers. So we start to see that by bridging our concepts to new number systems, what we really need to maintain is the distributive law and nothing else. So how crazy an addition can we have if all we want is distributive law? Let's find out. Nathan's natural gas recycling goes around and collects canisters of natural gas and drains them, takes them on to a recycling center. In this process, they have to keep some safety alive. After all, these are explosive materials. The key rule is that we can't overpressurize the tank. But the second rule is we can't have this way too much for the truck to pull it. How do we put these two pieces of data together? A long story made short is that over many decades, several people observed that little tiny particles moving around in a space produce what we feel as a gas. And if you wanted to understand how much gas there was in there, you would need to add up the weight of all those particles. Unfortunately, we can't see them and we can't capture them in all one place. That's what makes them a gas. They're moving all around. But we were able to measure other things, external qualities that would predict how many particles were in there. This became known as the ideal gas law. The law we'll need is that pressure times volume is proportional to the number of atoms. This little fish symbol is for proportional. Proportionality means that there's some constant associated to the equality. A deeper study showed that temperature was also a factor, and so the constant today is divided into R and T, where R is the constant of proportionality and T is the measurement of temperature. Today it's known as Pivner or the ideal gas law. Now what this does for Nathan's recycling is it gives him a simple formula to try to make sure that he stays within reason. In particular, P1 plus P2 cannot exceed the maximum. But what is this plus? P here are the pressure gauges that we read on the individual tanks. Each tank has been used a certain amount. They have different pressures. There's also whatever we need to put into this tank. Let's start with the tank being empty. If I'm going to transfer the natural gas from both canisters into the larger canister, they must stay below the maximum that's allowed for the pressure of this tank. Otherwise, we'll cause an explosion. Standing back to assess the problem with particles in tank 1 and particles in tank 2, we're going to transfer all of them to this larger tank. In real life, you might be some behind. We'll consider that a marginal error. Once we transfer these particles over here, because this is a different volume, it could have a different pressure. And the only rule we have is that the sum of our pressures needs to be no more than the maximum pressure. To get the pressure that results in this, therefore, we take the volume of this larger space, V3, and we multiply it using Pivner to get the formula for the pressure. Let's say that the resulting pressure in this tank is denoted by P1 plus P2. I'm using a goofy symbol for plus because it's going to be an addition that we don't typically use. So box plus will be my name temporarily. Remember, for this story problem, R and T are constants. We're assuming everything's at the same room temperature and the gases are the same, so the ideal constant value R is also the same. Using the distributive law, we've now split this up into two partial sums that allow us to think about the original pressures that we see on the two smaller gauges. Finally, we solve for the missing sum, which we'll need to check our warning. Now, this addition isn't your common addition. It has these scalars associated to it. It's what we might think of as a weighted addition, or what mathematicians call an affine addition. Variations on this theme might include adding an extra constant, for example, to model the idea that there was some gas already in here, or that not all the atoms get removed. Crazy affine sums like this are generalizations of what we see when we can't necessarily measure the content directly, but we measure with proportionality and we try to explore the original concept through these external measurements. This makes these enormously powerful and common types of sums to have in real life. This one, for example, could represent a storekeeper who offers you for the first purchase full price, but if you sign up for a $20 membership fee, your next purchase will be half off. This would be a simple formula to implement, and you probably wouldn't need to call this a new addition. But we're here to explore what happens when you take such additions on. These additions are quite common, but they don't behave as well as you might expect. No better way to see that than to put some numbers in. Now, in a normal number system, if I add 0, I don't change the number. But here we're going to see that that doesn't happen. 5 plus 0 now equals 25. That's a peculiar result. We're not expecting it. We can also see that we can't change the order of addition. If we were to continue on, we would see that we can't add without parentheses either. At this point, even though this was a motivated addition, you might start to wonder whether you really want to use it versus the addition you already know. If none of the properties you expect are familiar to you, you may want to back off. But before you give up entirely, let me remind you that subtraction is a very common arithmetic tool that also failed to have any of these properties. The same things could occur with division and many other numbers. We can actually show that the distributive law only cares about one specific rule, called the medial law, and these things haven't. If we stand back to see what Nathan has to do on a daily basis, is to take the two pressures measured on each tank, add them together by this formula, and see that it's less than P max. And to continue the algebra further, I could say that the weight per gallon could be computed from the ideal gas law by saying that the weight is proportional to the number of atoms. But if I want weight per volume, that would mean it's proportional to the number of atoms divided by the volume, which is the same as P over RT. RT are now constants. This makes it a function purely of the pressure gauge, and therefore Nathan can use it to make the volume prediction of the total weight per gallon. It might be instructive to pause the video and work out the mechanics of the asserted equation here. But if you trust me, we can move on to the point of this. In real life, we could assume that perhaps Nathan has a software package that does these arithmetic steps for him. But the key idea is still the same. Nathan should only be concerned with making one measurement, the measurement of pressures of the various gauges. This should be enough information to predict all the other aspects that are necessary for making decisions on the job. When we abstract a problem like this and we look at just the arithmetic that occurs when we only look at the indirect measurements, such as pressure, but we're trying to measure ideas like the number of atoms, we often find that we have to rescale in this similar way. But we still want to preserve the kind of algebra that we expect, such as distributive type qualities, that the material is somehow spread around. But the proportionality changes exactly what addition should mean. Now, the ideal gas law might appeal to you if you remember aspects of chemistry, but you might be interested in other problems. Perhaps you're interested in business or economics. There, too, you'll find such indirect measures. For example, we might look at the law of supply and demand. In a story like prices, we can see that the price change is proportional to inflation. If inflation goes up, the prices go up. But supply and demand are also related by an inverse relationship. The larger the supply, the lower the prices. But that has to track with the growing or decreasing of inflation. So we get a similar proportionality. That means that if what we can measure in our stores are the prices, we can still use this proportionality to get information on the supply. Likewise, if what we can measure is supply, we can get information on the prices using these proportionality rules. However, the results will be that the arithmetic distributes similar to what we saw over here. We'll have these different scales and different weights, and so we should be prepared to work with arithmetic that deals with such additions and to refine them. Moving to electronics, we can find two other types of addition. This squiggly symbol is what's known as a resistor. It's a measurement of how much is impeding the flow of the electrons. Now, every single wire impedes it at some amount, so there's never a zero resistance. And if we were to cut the wire, then nothing gets across. It's a perfect insulator. We'd call that infinite resistance. So our values are between 0 and infinity. In our first model, we see that the resistance simply adds up. We first impede it by R1 and then by R2. The total resistance is the same as R1 plus R2. In the second model, this is what's known as a parallel circuit. Here, as the current comes along, it can divide and go in both directions. And you can imagine that there would be some choices to be made. If this one was less resistant than that one, you could imagine more electrons go down R1 than around R2. And so we think of the total resistance as some formula relating to R1 and R2, but not simply adding them together. We'll invent a new addition. Here, I'm going to call this parallel addition. Kind of cute to put parallel lines around the plus sign, right? On the other side of this, we can use something known as Ohm's law to solve for the resulting resistance. It's a crazy formula, but it still works. Just like systems like the ideal gas law or supply and demand can mix up our addition and cause us to rescale it, so too, other systems in science and engineering can cause us to have other additions that behave in peculiar ways as well. But this doesn't mean that they're any less exempt from the process of calculus. We still might want to distribute concepts around this. After all, we're distributing the electrons on both sides of the circuit. So here's another source of distributable sums for the nerds. This is what's known as an elliptic curve. It's an equation that, like a parabola, has a particular shape to it. And the particular shape here is that we have a quadratic y squared compared to a cubic. Elliptic curves have been studied for a long time because they're on the boundary between easy and hard types of geometry. The techniques, however, turned out to be very useful in certain forms of cryptography. Well, the property I want to focus on is what's known as the elliptic curve addition. I take 2 points on the curve and I connect them by a line. The line lives in the larger plane. They won't be on the curve. In the drawing I just have here, I see that this white line intersects my curve somewhere else. This new point is given the name P plus Q. This addition is in fact distributable. That is, it satisfies the medial law. You can use it with a distributive multiplication. And there are several multiplications that do that, like the Tate and the Fay pairing. Now, if you look in many books, there's one other trick that mathematicians use to extend this to a better type of addition. That is one that is associative and commutative. This one by itself is not. They work through a tangent line through that point to get a second point, and that second addition cleans up the addition. This is often the case with medial additions. Even if you have a strange addition, it's often just a twist of some better known addition, such as a rescaling kind of thing. So you might choose to do that rescaling first and work with a better addition. But the reality is that the problem presented to you comes with the addition that it comes with. And the fact that you can model its distributive properties through things like integrals is backed on the fact that this is a distributable sum. Nevertheless, these rules are very powerful when they're around, and so we would like to exploit them if possible. Let's add one other condition that shows us the medial law is not too far away from having these two conditions. The following theorem, known as the Eckmann-Hilton argument, is one of the ways that we encounter such nice additions in real everyday life. Once we have a distributive product, we're forced to have a medial law. Therefore, the first law is somewhat common, but the second common property is the zero law. If we're lucky enough to have a zero, meaning a number that will be added to x equals x on both sides, then it turns out that we can recover these two very nice laws, the commutative and associative laws. These two properties are very common, and they allow us to draw parentheses. These are the additions that you've grown up with. They're the ones that we use most commonly. If we have any storyline where things are distributing and we are lucky enough to have a zero, then we get these two properties for free. We don't have to check anything. Don't take my word for it. Let's plug it into the formula and see. We cleverly choose where to put our zeros. For the commutative law, I'll put them in the opposite two corners. Then I rearrange my columns into rows. Standing back to look at what we have, 0 plus x should just be x, and y plus 0 should just be y. Meanwhile, 0 plus y and x plus 0 become x and y as well. Remember, our writing it in a vertical and horizontal shape is simply to help us remember what's going on. If we flatten everything to a straight line, we now see that we have x plus y equals y plus x. If you want to make sure you understand this, try to make the same rule for the associative law. That is, substitute values of x, y, and 0 into this grid and try to see if you can arrange the rows and columns in some way that end up producing this relationship. I promise it'll work out, and it'll be a good experiment for you to try if you understand this. So we've seen that the type of addition that we need in order to have a distributive product has to be distributable, or what technically is known as medial. I'll use distributable to remind us of the goal of this addition. Because of the Eckmann-Hilton argument, this divides into two kinds. If we have a zero, then our addition happens to have further nice properties, like it is associative and commutative, the kind of addition you probably used before. This would include addition of natural numbers, decimal numbers, complex and rational numbers. But it also includes addition of polynomials and matrices and many other structures that you've probably seen or will see soon. Further examples go into other areas, such as electronics. We can add resistance in series, or in parallel, we get two different types of additions. Both of them happen to have a notion of a zero. In serial resistance, the zero is played the role of a single wire. This isn't quite accurate. A wire has some amount of resistance, but at the granularity of most electronics, the wire is considered to have zero resistance, or at least negligible enough that it won't affect our calculations. In parallel resistance addition, it's the opposite situation. What we want to do is stop the flow through one of the two wires. We do that with an open switch. If we put the open switch on this bottom path, the only flow is through the top, and so the resistance is equivalent to whatever this top one is. It's as if we added zero, but we're using a different number for it. We think of it as infinite resistance. Examples of uncommon sum include things like our pressure gauges. If we took our two pressures and added them up to see if we did exceed the maximum pressure, we would see that we needed this goofy formula. So we can still use the calculus with it, but with much more hand-holding. Let's go back to our vanilla integrals. We saw two types of distributive law. One corresponding to adding a function f with another function g, and the other one having to do with the intervals being added together. That gave us the disjoint union. If we stare at the disjoint union, we put it in the common sum rule because all we need to do is see if it has a zero. What interval could we add to another interval and not change it? Well, the empty interval. Once more from the Eckmann-Hilton argument, we're guaranteed that this is both associative and commutative. What this means is that we can divide up our interval into several parts and not worry about which one goes where. We can commute the integrals on each of these individual intervals and sum them up in any order we like. There's one major thing left to consider. Most of us don't want to do addition by hand. We've given it over to computers. And by so doing, we've asked the computers to be good with their time. And computer engineering has gone to the extreme to make sure that we don't waste compute cycles. It is now the case that computers batch together large sums and collectively add up multiple things all at once. But they can only do this if they have a guarantee that the results will be the same based on how they restructure it. What they need to do is have a property that's similar to some of these rewriting rules that let us regroup the additions in some way that they're integrable. The whole is the sum of their parts, provided you can describe where the parts are and in what order they should be summed together. These days, we send most of our arithmetic to computers, and so you might encounter sums something like this. You load some data from some files or some computations, and then you simply ask for the sum. The syntax might change, but the idea is still the same. Notation like this is very common, but it can be a little bit surprising how much information is hidden from view. For example, why is data something that we can add up multiple things with in the first place? We must be thinking that there's some structure behind the data, something that encodes what the data pieces are. So we might, for example, have this as a function on some set of values. What's going on here is that data is a function on a data type I into something that we call numbers, and we access it usually as data bracket I. In mathematics, we might convert this to a single symbol, like delta, mapping from I into some number system, like the real numbers, and we might access that with subscripts, delta sub I. The sum is then converted in mathematical notation to the large sigma, summing over the little i's in big I. But this can be misleading. This type of addition doesn't tell us exactly how we're going to break up the sums into pairs. And here comes the nuance. When we describe this mathematically, we often simplify the story and assume that what we really mean is to add up in pairs, and that you can rearrange this however you like. That's making some strong assumptions about our addition. We've already seen that distributable additions are not required to have arbitrary regroupings. They might have some regroupings, the distributable ones, the medial ones, but they may not be associative and commutative. So there may be some requirements to have extra structure on I, such as a tree that describes exactly how to pair the things together, and that has to be respected. Otherwise, we might allow the computer to restructure the addition. In fact, most modern computers don't bother to add just two numbers at a time. They'll take entire batches and add them in large clusters. And you do the same thing in your head as well. Let me demonstrate. Add these three numbers up as fast as you can in your head. My prediction is that you added the 7 and the 3 first to get 10 and then got 29. That is, our minds are so coached to find shortcuts that we're free to rearrange them and find short advantages to the arithmetic. Computers do even more than we do in this process. There are entire methods called polytope methods and other optimization schemes that go through code and rearrange the order in which arithmetic is done to advantage it as much as possible. This makes code much faster. Over the years, those of us working in computation and mathematics have started to address the idea of multiple sums happening at once as a black box. Rather than detailing that everything needs to be reduced to binary operations with specific rules, we'll just simply take a sum as a clump. The standard notation for this varies from one place to another, but to avoid confusion, we typically use some new notation. I'll be using the integral style notation. This allows me to put weights on the different sums. This integral style notation is really just hiding the fact that we need to take a sum of a number of things. This captures all the data we need to know to perform a sum. We have I, which is the index set over which we'll be doing our sums. This could be an interval if we're doing a classical integral, or it could be finite numbers that we're adding up. Delta are the actual values, and we fetch them by delta sub I, or if in computer code, we'll write it as data. The dmu is a way of articulating the fact that we need to have some organization for how we're performing this sum. This could include things like rescaling. For example, when we saw the addition of pressures, we needed to rescale the right values to get the correct sum. Those values are now inside of these measurements. The total sum is taken as an abstract symbol. We don't care how the computer bothers to compute it. It can do it all at once, similar to how we would add three numbers by taking whatever advantage shortcuts we could see in our minds. The computer can do a lot of pre-calculations and predict that similar calculations could get the same result, but faster. Given this, we now think of a system of addition as having multiple versions of these integrals. All of them are describing different types of sums, but they have to play along nicely. What does playing along nicely look like in this notation? Well, similar to our distributable system, what we really needed to do was turn rows into columns and columns into rows. Well, now we just need to be able to intertwine our two integrals. Altogether, this is the systems that we really concern ourselves with when we program. Inside of our computers, we have numerous versions of various different sums. These range everywhere from simple sums that add the next one to each side to clever rewriting rules that structure it according to the architecture of the computer. They may also add rescalings in the middle for whatever the story problem is. The medial condition we saw at the beginning of adding rows or columns without changing the value is now repeated in the following general formula. If we add up over j's and then i's, it should be no different than adding up i's and then j's. This is a version of swapping the rows and columns, but now done on steroids. The rows and columns are now whatever possible different systems of addition we have. This could be many, even infinite. As long as they always can be swapped in any order, we're free to rewrite up to those rules. This accelerates our computations and allows us to group large computations as one black box addition. It's the modern way to think about addition. Similar to our Eckmann-Hilton argument, where we added a notion of zero and got a lot of mileage from it, we can add small extra details to this description of a distributable system and have extra power. For example, suppose that one of our sums in here is the good old-fashioned plus sign. Then we could substitute the plus sign for j and write it like this. Then moving to this side, the sum would come out. We've simply recovered the linearity property that we started this whole story out with. There are numerous other consequences of this formula that are similarly powerful. It's tempting to imagine that we can always retreat to just the standard plus sign to do all the arithmetic. After all, that's what got the idea started. But more and more of the computations are happening in large parallel systems, where the notion of pairwise addition is just no longer true. And in fact, it wasn't even true when you were doing addition of three numbers in your own head. So we need to be relaxed about the fact that addition is a broader family of things, but they do have to collaborate in nice ways. This is a grown-up version of associative and commutative. And as you program more and more things, you'll start to describe things like a print queue, adding things to a print queue, How does it distribute? Perhaps the first job that has to print takes longer than the second job as it warms up the printer, or the last file has to close all the sockets and it takes longer still. These kinds of nuances can now be part of your addition model, and yet they still behave well with the calculus. They distribute, and therefore they're integrable systems. Use this and you'll not only program better, you'll have a better calculus. Until next time. That's how you take care of your chalkboard.